Hi everyone, hope you are all doing fine. So how you find organic chemistry? Is it easy? Hope it is easy for you. Okay, so we're moving on to the next session, that is mechanism. So we have studied the chemical reactions, and there are three chemical reactions. One is nucleophilic substitution, then elimination reaction, and the third is reaction with metals. And we were discussing the nucleophilic substitution. So I told you, you have to study the mechanism of this nucleophilic substitution. And we said, since a nucleophile is initiated by this reaction, it is called as a nucleophilic substitution. It is a substitution. Okay. So we will see the mechanism. What is the mechanism behind this nucleophilic substitution? Okay. So we will see the substitution nucleophilic or nucleophilic substitution reaction. Okay. Nucleophilic substitution reaction. Nucleophilic substitution reaction is the mechanism are of two types. One is SN1 and second is SN2. See how I wrote? You are telling nucleophilic substitution, but you will be writing like SN. N will be small n. Okay. Then in 1, which means substitution, this is read as substitution nucleophilic unimolecular, and this is substitution nucleophilic bimolecular. Got it? So two types of mechanism comes in this, and there are so many criteria by which whether a molecule react with a nucleophile to form a desired product, or what is a desired product by this reaction by a nucleophile. Okay, so there are two types of substitution. One is substitution nucleophilic unimolecular, and second is substitution nucleophilic bimolecular. Now we will start with the substitution nucleophilic bimolecular. Okay, the mechanism behind the substitution nucleophilic bimolecular reaction. That is, we are starting with SN2. Okay, we are starting with SN2 mechanism. So what is SN2 mechanism? As I already told you, this is substitution nucleophilic bimolecular mechanism or bimolecular reaction. So what do you mean by bimolecular reaction? We will take an example for this. For example, CH3Cl. You are studying haloalkenes, isn't it? When the CH3Cl is treated with a nucleophile, hope you have written that table in your book, isn't it? Okay. So when a nucleophile like OH minus is attacked by a CH3Cl, what you will get? You will get the Cl is replaced by OH minus. Okay. So substituted to this CH3, and you will get CH3 OH plus Cl minus. So the halide ion gets separated and the OH minus gets in connection with this alkyl group, forming the desired product, that is CH3OH. Now the question is this reaction follows SN1 mechanism or SN2 mechanism? Or will both mechanism is related to this, or is SN1 is faster in this case or SN2 is faster in this case? So many questions formats can be asked like this. So first we will see what the mechanism is, and then we will for the questions. See, in this case I am saying this follows an SN2 mechanism. What is it? SN2 mechanism. Okay. So CH3Cl, and you know this is a primary carbon atom, right? That is CH2, isn't it? CH2Cl, that is CH2 is a primary carbon atom. So the CH3Cl plus OH minus will give you CH3OH plus Cl minus. Now we will say, I have already told you this is a substitution nucleophilic bimolecular reaction, which means that the name itself states that bimolecular means what? In the reaction, the two molecules take part in the reaction. That is called as bimolecular reaction. So which means what? both the CH3Cl as well as the OH minus take part in the reaction. Take part in the reaction means what? Which means that the rate of a reaction is determined by kinetics. Both the concentration of CH3Cl as well as the OH minus. Isn't it? You got it? That is, the rate of reaction is bimolecular means what? It depends on, the rate depends on both the reactants. If it was depending on only on the one reactant for say CH3Cl, we say it as unimolecular reaction or monomolecular reaction. Here, since it is a substitution nucleophilic bimolecular reaction, it states that in this reaction, or if this reaction has to happen, the rate of a reaction determines, or the rate of a reaction depends on both the concentration of this reactant. That is, if for example, if I say rate is equal to K into concentration of CH3Cl and concentration of OH minus. But just the kinetic says like that. So it says that the kinetic says it depends on both the reaction. Then what will be the order of the reaction? Tell me. What will be the order of the reaction? This is 1 and 1. So what will be the order? It must be a second order kinetics. So you can say the first point to be noted is it is a bimolecular reaction, isn't it? It is a bimolecular reaction. It itself says that the two molecules are taking part in this reaction. So what happens to that? The rate of a reaction depends on both the concentration of the reactants. So what will be the order of the reaction? It will be a second order kinetics. So the second point is it is a second order kinetics. Okay, it is a second order kinetics. Got it? Now we will see how the reaction happens. Okay, I will give a structural thing. Okay, a structural picture, a pictorial representation of how it goes. Okay, I will give a picture like CH3Cl, you know, it is an sp3 hybridized state. So sp3 hybridized state means what? It is having a tetrahedral structure. So if I want to show you a tetrahedral structure like this, see, it is a tetrahedral structure. Okay, one like this, and one like this. Now here the carbon atom is in the center. Okay, the carbon atom is in the center. Then one bond, then tetrahedral, no, two bond, the third one, and the fourth one which is going into the board. Okay, so inside it. So this is tetrahedral structure. Okay, so if I make it like, see, this is this structure. Now I am picturing it into a more comfortable way in which the nucleophile can attack. See, in this case, if I draw like this, the nucleophile will attack, for example, if this is a nucleophile, the nucleophile will have a chance to attack like this, isn't it? So here there are space, it is spacious. So I am going to revert this like this. I am going to draw like this. Okay, so this will be C, this will be the hydrogen, this will be the again hydrogen, this will be the hydrogen. So it is CH3, and this pointing this towards my left, that means towards your right, is the Cl. Got it? Just to visualize that, the pictorial representation. See, if you want to just have a tetrahedral like this. The junction at C, this is Cl, and the 3 are hydrogen atom. Okay, sp3 hybridization. But why? Because this is CH3Cl. Now, if a nucleophile is getting attacked, in what way it will get attacked? If like this it will get attacked, there is a chlorine atom, hydrogen, hydrogen, hydrogen. Even though hydrogen is small, still it comes, but the more convenient way for a nucleophile is like this it will come. So in order to have a pictorial representation, I am putting like this, which means what? I am drawing like this, that is C, 3 hydrogen and chlorine, and you visualize the OH minus this is a nucleophile, KOH or H2O, whatever. Here from this OH minus is coming and attacking in this direction. Why? Because if this OH minus is coming in this direction, there is a clash, because here there is a Cl. Got it? So whenever a bond is happening, in this reaction, the nucleophile or whatever the reagent, they will see in which direction it is comfortable. That is a mechanism. Okay, so that is a collision theory states. Correct. So the proper orientation, see, That is why you haven't thought about that portion is deleted. Okay, so that is why, see, whenever a reaction, we say that an effective collision happens, proper orientation is there. So here the proper orientation is, see, this is a nucleophile, it will come and attack like this, so that there is huge space here, and you know hydrogen atom is very, very small. So it is enough space to comfortably attack this and make the bond. Correct. So then what happens? See, first I will tell you the pictorial representation, that visualization, then I will draw it on the board. So you know it is like this. So this is the carbon atom at the junction, 3 hydrogen atom, and this is the chlorine. So that is CH3Cl. So if I draw like this, you will have Cl, this is the C, and this is the H and H. This H I represent like this dotted lines, which means this is inside the board, the 3-dimensional. It is like this. It is inside. This is inside it. Okay. So that is the representation. So you clear? Now we know what is a nucleophile. OH minus ion is the nucleophile. So OH minus will come like from this position. See, OH minus is coming from this position. So why it is coming from this position? Because it is easy for the attack. Because see, if the OH minus is coming like this, it will clash with the Cl minus. So the possibility is there. Or clash means what? There is no, the collision must be not effective. The proper orientation is not there. Okay. So the energy, the activation energy will be very, very high. So what happens? Since repulsion is taking place, so many things, because this is Cl, it goes by Cl minus, isn't it? So the minus and minus will repel. So many factors are there. So what will happen to this OH minus? It will comfortably go to this side and it will go and attack. Here there is no collision because this hydrogen atom is on inside this board. So this here it is free. That is why I told you it is like this. See, it is like this. See, it is like this. That is, this is chlorine atom, this is first hydrogen, hydrogen, hydrogen. See, this space is free. So the nucleophile can attack from this position. So now hope you understood the visualization. Okay. Now what happens? Now this OH minus comes in attack. Now what happens is, then there is a state whether, okay, there is a state whether a simultaneous breaking and making of bond happens. See, what happens is, in this case, see, okay, just see the structure or geometry, how I am drawing it. So here there is, see, the instability of this bond. Here it is OH and here there is Cl and this is H. See, this state is called as transition state. Transition state means what? Before going into the product, a state will be formed where here the making of this new OH bond happens at the same time. That is, simultaneously, what happens? This Cl minus bond will break. And this state is highly unstable. You cannot isolate this state as, okay, this is not an intermediate. When you will call an intermediate, we will say in kinetics, I think, in the reaction of H2O2, hydrogen peroxide, by a catalyst iodide, there is an intermediate formed, IO minus, if you are remembering. So that is intermediate. Intermediate means what? A step is there, the reaction is happening. We can isolate that product. So but here, you cannot isolate the product. That is, it is simultaneous. Within a fraction of second, what will happen? The Cl minus will go as Cl bond will break and go as Cl minus. And what will happen? Then this OH bond will come and form. So now what will happen? Now what will happen is OH bond will form. So what will happen? The C, then this is H and H. And this is the OH bond. See? So this happens. So in this picture or visualization, what happens is, I can tell you, this transition state is like this. See? The transition state is like a trigonal planar, and from both position, there are what? In both position, this is OH and this is the Cl minus. So this is the transition state. And it is highly unstable. Why? Why? Because see, count the number of bonds 1, 2, 3, 4 and 5. So it is definitely unstable. So what happens? And I told you this is not an intermediate. There is no intermediate formed in this reaction. What do you mean by intermediate? You can isolate or really the reaction is happening. So here there is no reaction happening. Just a state transition. You say, no. For example, if you are flying from, Trivandrum to Delhi, there must be a transition in Bangalore or in Bombay. The flight will be having a transition. So we have to get down, then you go into another flight. So that is a transition state. So in that case, what happens in the same thing, we are telling just simultaneously what happens, this OH bond will be, this Cl bond will be breaking, and this making up of the new COH bond. So what happens is, can you see any difference in this geometry of this making of this COH bond? Can you see any geometry? There is any difference in the geometry? That is, this was the Cl, isn't it? This was the Cl geometry. That is 3, this thing and this. But when after the attack of a nucleophile, see, after the attack of a nucleophile, the geometry is inversed. See, this is the carbon-oxygen bond is in the, for my side, it is in the left side. Okay. And all other carbon-hydrogen will be on the opposite side of the first thing. See, very, very important point. That means here, this will be like this. See, this will be like this. I am drawing like this. Now, after this transition state, the OH bond makes and breaking up of the Cl bond. See, this will become like this. That means an inversion of configuration happens. See, an inversion. It was like this, and this was chlorine. When OH minus is attached, it becomes like this, which means the OH minus is coming from this side because chlorine was there. So if it is in this side, the structure gets what? Reversed. Isn't it? It was like this, pointing, the hydrogen is pointing to me at the time of the reaction, at the starting of the reaction. But at the ending of the product, who is pointing to me? The OH is pointing to me and the carbon hydrogen is pointing outwards to me. Which means that there is an inversion of configuration. You got it? It's very, very important. So, whenever there is an SN2 mechanism happening, whenever there is an SN2 mechanism happening, what will happen? There is an inversion of configuration. Like when there is a strong wind and you have an umbrella in your hand, what will happen? The umbrella will, that umbrella portion will be moving in the opposite direction, isn't it? The wind. If it was like this, it will become like this. So, exactly like that, there must be an inversion of configuration in an SN2 mechanism. Hope you have understood what I have tell you in the pictorial representation. Okay, you just make your own. If I have a ball and stick arrangement, I can very well show you. But this is also okay, I think. Okay, so just go through it. Okay, you have to make your own inversion of configuration. Just see whether you can have that. Okay, so now, so we can say, once again I will tell you, SN2 reaction means substitution nucleophilic bimolecular reaction. It's very, very important because they won't ask you just like that, what is an SN2 reaction or what is the kinetic of SN2 reaction? No, they will give you an example, a compound, and ask you whether this compound follows an SN2 or an SN1 reaction. Okay, so this is SN2 means substitution nucleophilic bimolecular. What was the first point? Since it is a bimolecular reaction, we can say the two molecules or two reactants are taking part in a chemical reaction or in a nucleophilic substitution. Now, second point, what is that? The order of reaction is 2. So, or it follows a second order kinetics. Okay. Now, what was the third one? No intermediate is formed. Isn't it? Only a transition state is formed where the making of this OH bond or the nucleophile and the breaking of the halide ion takes place simultaneously. There is no time lag. Just the bond is getting attached, the halide bond is getting detached. So that is called as a transition state. That's the difference between a transition state and an intermediate. Intermediate means we can isolate that molecule or the compound. Okay. So there is no intermediate formed. In the transition state, the making and the breaking forms simultaneously, and the halide ion is given out. And the very important point is, in an SN2 reaction, always there is an inversion of configuration. That is the main point. Okay, so there is an inversion of configuration, and I hope you have understood clearly what is an inversion of configuration. We will study more in this chapter, in the stereochemistry, what is inversion of configuration. Okay, hope you understood this much. Now we will see what is the reactivity, or what is the order of reactivity for an SN2 mechanism. Okay, we will see that. Hope you understood this. So any problem, just give me a call. I will make you very, very clear. Okay. Now we will see the order of reactivity. You know, there is a primary carbon or a primary group or a secondary group or a tertiary group. For example, if I say, or if we can relate all this, if it is a CH3Cl, okay, I may say it's a CH3Cl. There is a CH3 twice CH3Cl, then CH3 twice CH2Cl, correct? Sorry, CHCl. Okay, so this is a primary. Okay, this is a secondary CH, and this is a tertiary CH3 thrice CCl. If you one more I can write CH3 CH2Cl. So 4 compounds I can compare. See, 4 compounds I can compare and say the reactivity. Okay, now just imagine CH3Cl. Just imagine CH3Cl. What we have said, we have this much. That is, this is CH3 and this is the Cl. Correct? See, this is the imagination. That is, the center is a carbon atom. This is the 3CH bond and this is the Cl. Now, as I already told you, the hydrogen atom is very, very small, isn't it? Now, in CH3Cl, the coming of or the incoming of the nucleophile is very, very easy. There is no steric hindrance because you know the hydrogen atom is very small. Primary carbon atom, isn't it? This is a primary carbon atom. Why? Because CH3 can be also written as HCH2Cl. Am I right? HCH2Cl. So this is a primary carbon atom. So keep in mind, for primary carbon atom, the easiness is, or the coming of the nucleophile is very easy. Okay, when compared to, for example, I am taking this hydrogen atom and putting a more bulky CH3 group. That is called as CH3 CH2Cl. See, CH3 CH2Cl. So this is a bulkier CH3 atom group when you compare with hydrogen, but still it is a primary. See, it is a CH2 group. Even then, the coming of a nucleophile is easier. When compared to hydrogen, it is difficult, but still it will be easier because only there is one CH3 group. You remember C to C bond, then there is hydrogen bond. Just imagine, there is a picture in your book, just go through it. Okay, now this is a CH2 group. Since again this is a primary group, still the coming of a nucleophile is easier. But when compared to this, it is difficult. But when this is also removed, okay, and again a bulkier CH3 group is put, sir, this is bulkier, no? So this is put. Then what happens? See, these two bulkier groups of CH3 are there, which means this is carbon, 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 carbon. Again there are 3 hydrogen atoms. Now, then the coming of a nucleophile or the attacking of a nucleophile with these two bulkier CH3 group is difficult, isn't it? The steric hindrance will come. So, for a secondary carbon atom, see CH, secondary carbon atom, it is difficult than the primary carbon atom, isn't it? And then you imagine, you knock out this hydrogen atom and again get, this is again bulkier one, no? Again a bulkier CH3 group is there, see, a bulkier CH3 group is there. So all the 3 CH3 group with 3 hydrogen, 3 hydrogen, 3 hydrogen here, 3 hydrogen. So it is very, very difficult for the incoming nucleophile to get in and getting bonded to, but it still happens, but the reactivity order will be, it still happens because it will go and kick it, no problem. But if you compare the reactivity, the reactivity will be in the order of, now you can say what, the primary carbon atom or the primary carbon atom molecule of the compound will be greater than secondary, which will be still greater than tertiary. Or the primary carbon atom will follow an EC SN2 substitution rather than a tertiary carbon atom. Okay, so the question will be asked like this. You are given 2 compounds CH3CH2Cl and CH3 tri-CCl. Or out of these 2 compounds, which one is faster in SN2 mechanism? See how the question comes. You are given 2 compounds or 3 compounds. If you are given 3 or 4 compounds, like see 4 compounds, and they will ask you arrange the ascending order of the reactivity for an SN2. So what will be the order of reactivity for an SN2 mechanism? Tell me. Primary, these 2 are primary. When comparison comes, this will be easier. But still, primary greater than secondary, greater than tertiary. So that is the order of reactivity of an SN2 mechanism. Hope you understood. Okay. Now we will write the value points of this SN2 mechanism. Okay, just listen. The value points for the SN2 mechanism. Okay, so please write it down along with me. That is SN2 mechanism. Okay. SN2 mechanism. The first value point is, what is it? It follows a bimolecular reaction. So it is a bimolecular reaction. Okay, it follows a bimolecular reaction. These questions also asked for the board exam. The second is, what is it? It follows a second order kinetics. Okay, so it follows a second order kinetics. You know that. I have written it. Kinetics. Okay. Now third, if you want, you can write or you can make it as a point. Okay. No intermediate. No intermediate is formed. Correct? No intermediate is formed. And the fourth is, what is it? Very, very important. Very, very important. I will write it as inversion of configuration happens. So, inversion of configuration. I have given you a clear picture, I think. Okay. Or just do it yourself, how it comes. Okay. The inversion of configuration is a very, very important point. And the fifth one is, what is the fifth one? The order of reactivity. That is primary greater than secondary greater than tertiary. See? So, this is all about the SN2 mechanism. So, you got it? What is SN2 mechanism? That is substitution nucleophilic bimolecular reaction. Okay, once again I will sum up. That is SN2 is substitution nucleophilic bimolecular. From the name itself, you know it is a bimolecular reaction. Correct? Now, it is, since the both reactants are taking part, this, and also it can be bimolecular, or you can say rather than bimolecular, or again one more is can be there. That is sixth one. One more it is there. It is a one-step process. It's also important. This is a one-step process. Okay. Why? Because SN1 is a two-step process. Okay. So, it is a one-step. So, this has to be like here. From this here. So, it's a bimolecular reaction. It is a one-step process. Okay. Only one step. That is CH3 Br plus OH minus will give you CH3OH plus Br minus. That's a one-step process. Okay. Since it is both the molecules taking part, the order is second order. And you know there is no intermediate formed, only a transition state is formed. And what is the importance of transition state? Here, simultaneously the breaking and the making of the bond happens. That's the importance of that. Correct? And the very, very important point is there is an inversion of configuration happens. And the last one is, the order of reactivity is primary greater than secondary greater than tertiary. So I hope you understood very well. Now just you go through it and then write the notes on your own, taking an example and just get the value points. Okay. Clear? Okay. Now we will pass on to just SN1 mechanism also. Okay, just it is, now if you know this, it is very easy for me to teach you the SN1 mechanism. That is very, very easy. So we will see what is SN1 mechanism. If you are clear with SN2, just I can go on telling what is SN1, just having a description. So SN2 mechanism means, sorry, SN1 mechanism, the name itself, it shows what? The name itself shows that it is this is unimolecular, isn't it? Unimolecular reaction. I don't want to interpret on that, or I don't want to elaborate on that. You know, unimolecular means what? It is important, right? Unimolecular means only one reactant is important in this reaction, isn't it? Unimolecular, we have studied in kinetics, since these are kinetics. Unimolecular, bimolecular, termolecular and tetramolecular. Most of this stops with the trimolecular, isn't it? Elementary reactions, complex reactions, etc. So this is unimolecular means only one molecule. The rate of the reaction depends only on one molecule. That is the meaning of a unimolecular reaction. So again, the next point comes as such. What is that? Since it depends, or the rate depends only on one reactant, what is the order of the kinetics? What is the order of kinetics? It must be a first order kinetics, isn't it? Simple. It is evident from that. So the second point is, it is a first order kinetics, isn't it? Am I right? Simple. Only one molecule is taking part in the rate of the reaction. It must be a first order. If you want an example, I will give you. For example, we are taking here CH3 thrice CCl or Br. CH3 thrice CBr. See. Now, for some reason, I have taken this tertiary carbon atom. And I will tell you the reason also. Why? Because we have to get a carbocation here. Like what we have said in SN2 mechanism, the very important point is the inversion of configuration. In SN1 reaction, the very important reaction is the formation of a carbocation. What is it? So, it's a very important point, that is the formation of a carbocation. What do you mean by carbocation? That is plus, carbon with a plus sign. Okay, so you know that formation. So this, and you also know that a tertiary carbon atom will form a carbocation very easily when compared to a secondary or a primary, isn't it? So the next step will be what? The order of reactivity. What will be the order? Here the order of reactivity will be tertiary greater than secondary greater than primary. See how, if you know the SN2, it is very easy to format the SN1. Okay, I will give an example how the formation of a carbocation and all. First I am telling you the value points. So it must be the tertiary greater than, because why? Tertiary carbon atom is very easy to form a carbocation rather than a secondary or a primary. And again, we said SN2 mechanism follows a single step, ulta. SN2, one step. But SN1 mechanism, it follows a two-step reaction. 2 for 1, 1 for 2. So here it is a two-step process. See, it is a two-step process. That means it occurs in two steps. First step and second step. That's the meaning. Whereas SN2 means what? It is only a one-step process completely. That is, the two molecules are, the two reactants are taking part, the second order kinetics, just both reactants happens and the product is formed. But here the carbocation formation is very important, and there are two-step process, one and first step and the second step. And one more point, if you want to write, that is why in SN2 I have written, what is it? Inversion of configuration. Here I can say there is no inversion of configuration. So 1, 2, 3, 4, 5, 6. No inversion of configuration. See, no inversion of configuration is there. So these are the value points in an SN1 mechanism. Okay, now we will see an example how it goes. Okay. That is, an SN1 mechanism only happens, a very value point, important value point is, an SN1 mechanism always happens in presence of a protic solvent. Protic solvent means what? What will be proton? H plus. So, any solvent which is able to give out a proton is called as a protic solvent in aqueous solution. For example, water, acids, isn't it? Acetic acid, water, etc. all are protic solvents. That means it is capable of leaving the H plus ions in solution. That is called as protic solvents. Okay, so this SN1 mechanism always happens in the presence of a protic solvent. Now you know what is protic. For example, HCl, H2O, H plus or H minus, H is released. HCl, H is released. Okay, even acetic acid in that matter, CH3COOH. Again, there is a less amount of H is there, but still H is there. So, in a protic solvents, this SN1 reaction happens. So, whenever you make a note on this SN1 mechanism, always write only in presence of a protic solvent. Isn't it? Like H2O or HX. Now, what is the importance of that protic solvent? Okay, because only in presence of that, this reaction happens. So, you want to know. A board exam question came some years back. What is the role of the protic solvent in SN1 mechanism? Okay, for that we will write the reaction. That is, once again I will write you. Purposely I am taking the tertiary because it is easier, isn't it? It is more easier for getting the SN1 mechanism. So I am taking CH3 thrice C Br. See? You know the structure, right? 1, 2, 3, CH3, 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 Br. See? Only C is there. That is why this is called as a tertiary carbon atom. If somebody doesn't know it, just giving you an idea. Okay. So this is a tertiary carbon atom. Okay. Now, I have already told you it is a two-step process. So the first step is, see how I am writing it. See, I am writing like this. It is a reversible process, and you know kinetics, reversible, it must be a slow step reaction, isn't it? Reversible means it is a slow step reaction. Okay, so here I will get CH3 thrice C plus Br minus. See, so the first step, listen very carefully, the first step is the formation of a carbocation. See, the formation of a carbocation, and this is being the slowest step in kinetics. We already know that the slowest step determines the rate of a reaction, isn't it? Are you remembering? The slowest step determines the rate of a reaction. So, this step, the first step determines the rate of a reaction. Now going back, it is a unimolecular reaction, the first point, which means in this reaction, the rate of a reaction, if I say or if I write the kinetics, the rate is equal to a constant into only CH3CBr and not the OH minus or the nucleophile, where in SN2 we have also written the OH minus, isn't it? Getting me? Yes. So here there is only one. So since it is a unimolecular reaction, what is the order? 1. So that is, it follows a first order kinetics. You got it? It follows a first order kinetics. Okay. Now going back, we told that it only happens in a protic solvent. Okay. Now what is the role of the protic solvent here? I'll tell you. Since this Br minus, the C-Br bond has to break, isn't it? See, then only if the C-Br bond has to break, then only the C plus will come. isn't it? That means the carbocation will be there. So in order to get away or to weaken the CBr bond, what happens? If the protic solvent is there, this H plus, protic means this H plus, the H plus will get along with this Br. It will pull the Br. It will pull the Br and form what? HBr, and you will get what? You will get the carbocation. See? You will get the carbocation. So that is the importance of this protic solvent. Okay, that is the importance of a protic solvent. So keep in mind, this SN1 mechanism happens only in a protic solvent. Why? Because the protic solvent, the H plus will abstract the halide ion to form the corresponding HX, and readily you will get a carbocation. Okay, readily you will get a carbocation. Okay, so that is the importance of this protic solvent. Now, as I already told you, tertiary greater than secondary greater than primary. It is, and now what is the second step? The second step is nothing but, see, the second step is CH3 tries C plus plus our nucleophile. Whatever be the nucleophile, the OH minus nucleophile, you will get what? CH3 thrice COH. See? CH3 thrice COH. Okay. So, this is how you will have the SN1 mechanism. Got it? This is how you will get the SN1 mechanism. So, what are the value points for the SN1 mechanism? That is, it is a unimolecular reaction. It is a first order reaction. The formation of a carbo, this is very, very important, formation of a carbocation. And what is the order of reactivity? It is tertiary greater than secondary greater than primary. And it is a two-step process. Okay, you know, first step is the rate determining step. From this step itself, you know that this follows a first order reaction and it is a unimolecular reaction. It happens only in a protic solvent. Why? Because the H plus of these protic solvents will abstract or get away this halide ion, which makes the CBr bond very weakened. You see, and then very easily you will get a carbocation. Now once the carbocation is formed, then the second step happens. And easily it will form what? OH minus. Okay, so that is the mechanism behind it. Okay. Then here one more thing is happening, the hybridization is happening, see, or in the geometry, listen, in the geometry what happens is, I will tell you, in the geometry, you know, CH3 thrice CBr means what? If I have a geometry like this, what we have said, this is CH3, okay, one here, and the other here, right? See, this is our CH3. This is a bulkier CH3, this is a bulkier CH3, this is a bulkier CH3, this is a CBr, right? This is a CBr bond. Okay. Now listen. When this protic solvents, from the protic solvent, the H is coming and attacking this Br bond is getting, so this is a tetrahedral shape, right? It is sp3, isn't it? One tetrahedral, correct? It should be somewhat like this, but for the easiness I am telling like this, okay? I know you know that, correct? Okay. The tetrahedral arrangement, so this is like this, correct? Now this is the Br. These are the bulkier CH3 group. Now what happens? The hydrogen ion, the proton, the protic solvent contains the H plus ion, okay, very small H plus ion, okay, just imagine this is H plus ion. This comes and get this bromide ion as HBr, it will go off. Then this tetrahedral structure will come as a planar, triangular planar. See, that is the beauty of this mechanism. The tetrahedral structure, that means this is a tetrahedral structure. This tetrahedral structure is converted into a 120 degree planar. 109 degree 45 minutes is converted to a 120 degree. Okay, in the plane. That is the first step. planar. Okay, so sp3, I mean the tetrahedral shape is getting into a planar shape. And then simply the OH minus can attack from the two sides, right? See, this is a planar, like this, it can come. The OH minus can come like this without any difficulty. At the same time, the OH minus can come in this line also, because it is not tetrahedral. The steric effect comes, isn't it? So, what is the main thing behind that? You have to get a carbocation first. That is the funda. The more easier the carbocation formation, the more easier the SN2 mechanism. Believe me. That is the concept. So, the order of reactivity is therefore tertiary greater than secondary greater than primary. So, hope you understood. Here the geometry changes. That is again a point. That is from a tetrahedral to a planar shape. So, it is very easy. Both directions you can come. See, this is a planar structure. Equilateral triangle in a plane. It can come from this position OH minus. At the same time, with same easiness, it can come from, there is nobody to hinder. There is no steric hindrance. If at all, if it is CH3 group also, it is in this sides. It can very well come in this position. Isn't it? So, that is the mechanism behind the SN1 reaction. Okay. So, today we will be having these two, SN1 and SN2. Just go through it very seriously. Make a note of your own. Any problem you just come back to me. I will give you the answer. Okay. So, I hope you have written the exercise questions in text. Hope there is no problem with all that. Okay. If any problem, tell me. Or I will give you a Google section for that in small divisions. Okay. So, small sessions we will have that to do the exercise questions of this organic. No problem. Don't worry. So, till then, thank you.